Hi, folks. In the last section of chapter 9, we're going to be solving quadratic inequalities just in one variable. And what this means is that if we've got a graph of a parabola, maybe that looks like this, um, if we're trying to solve for an inequality um, of this form, then I'm looking for places where the parabola is less than zero. I'm looking for places where the parabola goes below the x-axis. On the other hand, if I am trying to solve a parabola that's greater than zero, I'm looking for values that are above the x-axis, like this. So solving these inequalities really depends on where those zeros are, where the solutions to the quadratic equations are. And then we're either going to look at parts of the parabola that are lower than and greater than those numbers, or we're going to look at regions of the graph that are between those two values. Also, just like we learned earlier in the year, sometimes we're going to include this data point in the inequality, in which case we're going to have to kind of color that point in because this point is included in the solution. And other times we'll leave an open circle there. And that's going to be the difference between, we'll use an open circle for when we have a greater than or less than inequality, and we'll use a closed circle. Let me color code this a different color. We'll use a closed circle when we have a less than and equal to or greater than or equal to sign. So let's look at how to solve a quadratic inequality algebraically. The first step for approaching this type of problem is finding the critical values. Where do the graphs actually hit zero? Where do the graphs equal zero? So I'm going to want to solve the quadratic equation x squared minus 3x minus 4 equals 0 to find me these critical values. You can use the same strategies that we talked about in section 9.4. You can solve them by factoring. You can solve them by taking the square root of both sides of the equation. You can solve them using the quadratic formula. Any of those strategies work here. I want the factors of AC, which is 1 times negative 4, which is negative 4, that sum to B. My B value is negative 3. So my factors of negative 4 that add up to negative 3 would be negative 4 times positive 1, and then negative 4 plus 1 equals negative 3. So if I factor this as x minus 4 times x plus 1 equals 0, then my x values are going to be positive 4 and negative 1. Remember the zero product property. If x minus 4, the quantity, times the quantity x plus 1 equals 0, then either x minus 4 equals 0 or x plus 1 equals 0, and therefore x equals 4 or x equals negative 1. Now, notice that I made both of these open circles because there's a less than sign here, not a less than or equal to sign. If there were an equal sign here as part of the inequality, I would color in those circles. Now, the question is, I don't know if I should be kind of shading this to the left and to the right of those zeros, or if I should be shading kind of the region in between the zeros. So what I'm going to do is test some values. I'm going to choose a number down here, like I'll test the x value, negative 2. and plug it into the equation and see if the inequality is true when I plug it in. So let me give you an example here. I want to do, I'm saying that x is -2, so I'm kind of doing f of -2. I'm going to do -2 squared minus 3 times -2 minus 4. And I want to know, is this answer less than 0? -2 squared is 4. -3 times -2 is +6. And then I'm going to subtract 4. The question is this less than 0? Well, 6 is not less than 0. This is false. So I am not going to shade to the left of this 0. I'm probably going to shade to the right up until the next 0 because I'm kind of imagining a parabola that does that and kind of crosses the x-axis here and here. And I want values that are less than 0. But just to make sure, I'm going to go ahead and plug in the number 0. So let me test 0 next, just because 0 is an easier number to plug in than 1 or 2 or 3. If I plug in if I have 0 squared minus 3 times 0 minus 4, is that less than 0? Yes, -4 is less than 0. So this is definitely the region that I'm trying to shade in here. And I'm probably not going to shade this upper region in, but let's go ahead and test the 5 value and see what we get. 5 squared minus 3 times 5 minus 4, is that less than 0? Let's see. 5 squared is 25 minus 15 minus 4. Is that less than 0? No, it isn't. The answer is +6, and +6 is not less than 0. This is false. So the only one that was true was this region, and so that's the region that I shade on the number line to kind of express when this quadratic inequality is less than 0. Let's do another example. X squared plus x minus 6 is greater than or equal to 0. Again, my first step is going to be to find the critical values, kind of solving this as though it were an equation to find what my x-intercepts are. In this example, once again, it looks like factoring is easiest or fastest. I'm going to say, what are my factors of AC that sum to B? So A times C is going to be -6, and I want those factors to add up to +1. And the factors that do that are -2 times +3. Those multiply to -6, but there's a +1 difference, a +1 if I add those two together. So that means my factored polynomial would be x minus 2 times x plus 3 equals 0. And so either x minus 2 equals 0 or x plus 3 equals 0, which means that either x equals +2 or x equals -3. So those are going to be my x-intercepts, my solutions to the quadratic equation. So -3 here and +2 here. Notice this time I colored in the circles, and that's because my inequality symbol has an equal sign included in it. And so it's okay if if the region that I'm shading in is equal to 0. The 0 is included in the solution. Okay. Next step, I don't know if I'm shading the region between these values or if I'm shading the kind of the extreme regions here. So let me choose a few test numbers. I'll try -4, I'll try 0, and I'll try +3. Let's plug -4 in first. -4 squared plus -4 minus 6, is that greater than or equal to 0? Well, -4 squared is +16, and then -4 is just -4, so I'm subtracting 4, and then I'm subtracting 6, so I'm subtracting 10 total. And so is that greater than or equal to 0? Yes, it is. 6 is greater than or equal to 0, so that is true. So I will be kind of shading my line down this way to the left. This probably means that my 0 is going to, if I plug 0 in, that solution won't work. 0 squared plus 0 minus 6, is that greater than or equal to 0? Well, no. -6 is not greater than or equal to 0. This is false, so I'm not going to color in that region between the two green dots. And now let's test this 3 value, which I suspect I will be shading in. 3 squared plus 3 minus 6, is that going to be greater than or equal to 0? Well, 9 plus 3 minus 6, that's going to be minus 3. And then, yeah, is 6 greater than or equal to 0? Yes, it is. So I am going to shade this region up here. Now, I am going to go back and look at the previous question because I want to be able to just not just express these as number lines, but also express these as compound inequalities. So let's look at both of these kind of together and remind ourselves how we write these as inequalities. If our x value is between, if our true range is between two values of x, we kind of write x in the middle. In this example, x has got to be greater than -1, but less than 4. So x is between those numbers. This is how we express this inequality algebraically. This is a compound inequality. Both of these statements are true. Both x needs to be greater than -1 and x needs to be less than +4. For this second example, this is not an and compound inequality. This is an or compound inequality. Either x is going to be less than or equal to -3, or x is going to be greater than or equal to +2. They can't both be true. A number can't be over here and over here. Either one is true or the other is true. So this is an or compound inequality. Just to kind of remind you of some of the things that we learned first semester. Right. So we solved those two inequalities algebraically. How can we kind of solve these graphing wise? To solve these graphing wise, you need to be able to graph the parabola indicated by the quadratic function. This example here is not easily factorable. There are no factors of -15 that add up to -1. So we are going to use the quadratic formula here to find our x value. So we're going to do x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a. So that means -1. Don't forget to have the negative from the formula as well as the negative as part of your b value. Plus or minus the square root of b squared. Well, -1 squared is just 1. Minus 4 times a, which is 3, times c, which is -5. All divided by 2 times 3. That means I'm going to have -1 is the same as +1, plus or minus the square root of 1, let's see, 4 times 3 is 12, times 5 is 60, and I've got negative times a negative, so that's a positive. So I'm going to have 1 plus 60. So I'm going to have 61 under the square root, and I'm going to divide this by 6. Because I'm trying to graph this, I don't want this written in kind of radical form. I'm going to go ahead and plug these numbers into my calculator and see what values I get. And my values of x are going to equal kind of -1.14 and positive 1.47. You could have also kind of graphed this on your graphing calculator and kind of use the trace function to kind of figure out what those x-intercepts are approximately. But here, negative 1.14 is going to be just past negative 1, and 1.47 is uh, um, about halfway between the positive 1 and positive 2. It's also really easy to get the y-intercept value here. I can find out when x equals 0, this term disappears, and my intercept is just kind of negative 5 here. So I know that my parabola goes this way, even though I drew it poorly. And I can now kind of look graphically at where is my parabola greater than 0? Where is my parabola above the x-axis? And I can see that my parabola is above the x-axis at kind of these extreme versions, when I'm less than that lower x-intercept and when I'm greater than that higher x-intercept. So I'm going to express this by saying all the values from this x-intercept, including that x-intercept. So I'm going to color in that circle and going this way. And all the x values from this x-intercept moving to the right are going to be included. And so what this looks like algebraically is either x is going to be less than or equal to negative 1.14, or x is going to be greater than or equal to 1.47. And we have now solved this inequality. Let's do another example. Once again, looking at how easy this would be to factor. 2 times negative 4 is negative 8. There are no factors of negative 8 that add up to 3. So this is best solved by using the quadratic formula. So I'm going to do, I have the quadratic formula written up above, so I'm just going to plug in my values. Negative 3 plus or minus the square root of b squared. Well, 3 squared is 9. Minus 4 times a, which is 2, times c, which is negative 4, all divided by 2 times a, which is 2. So solving for this, I've got negative 3 plus or minus the square root of, let's see, 9. Negative 4 times negative 4 is positive 16, times 2 is 32. So I'm going to add 32 onto there, divided by 4. And so if I just kind of plug this into my calculator now, plugging those values into my calculator, I get that x equals negative 2.35 and x equals positive 0.85. Again, alternatively, you could just plug this into the graphing portion of your graphing calculator and use the trace function to find out those approximate x-intercepts. But here, negative 2.35 is about here. Negative 0.85 is about here. Again, it's very easy to graph the y-intercept. If x equals 0, this term disappears, and my y-intercept is at negative 4. So I know my parabola looks approximately like this. And for this inequality, I want to know where my parabola is less than 0. So I'm looking at where my parabola is negative and hangs below the x-axis. So I'm specifically looking for x values that are between those two x-intercepts when x is greater than negative 2.35 and when x is less than 0.85. And again, here I'm using just less than symbols because my original inequality did not have any equal signs involved there. So graphically, I could graph this as an open circle, graph this as an open circle. and kind of graph the shade in the region between those 2 points. Why would this be useful? What's a real world example of why we might kind of solve a quadratic inequality like this? Well, in this example, an archaeologist is going to rope off a rectangular region of land to dig for artifacts. The region must have a perimeter of 440 feet. Maybe that's how long his rope is. Of course, the perimeter of a rectangle, if you think about the length and the width of the rectangle, you need to do the width twice and you need to do the length twice, and you need to add those all together. So that's the perimeter of the rectangle. And if you want to find the area of the rectangle, you just do the length times the width. So what we're saying is that if the perimeter, which is 2 times the length plus 2 times the width, needs to be equal to 440 feet. So 440 feet equals 2 times the length plus 2 times the width. And then the area, which is going to be length times width, needs to be at least 8,000 square feet. So 8,000 square feet is the area, and our area needs to be that at the very smallest. Hopefully their length times width is actually going to be bigger than that. So length times width is going to be greater than 8,000. What I need to do here, I can't solve an equation if I have more than one variable in the equation. If I've got more than one variable, then I need 2 equations to help me solve it. Here I've got 2 equations, or 1 equation and 1 inequality. So what I'm going to do is I'm just going to rewrite one of these variables in terms of the other. So I'm going to solve for W. I want to get W all by itself on one side of the equation. I could have chosen length, but I've just randomly chosen width. So I'm going to subtract 2L from both sides of the equation. And I'm going to get 440 minus 2L equals 2W. And I still don't have W all by itself. I want to divide by 2. If I divide both sides of the equation by 2, then I'll have W all by itself. To divide this side of the equation by 2, I need to divide both components by 2, each component by 2. So 440 divided by 2. In fact, I'll write this out as a separate step because students sometimes miss this. They want to just divide one of the terms by 2, but you need to divide both of the terms by 2. The only way that they can be together at the top of the fraction is if they shared a common denominator to begin with. So here I've written it as a separate subtraction problem. 440 divided by 2 is 220. 2 minus 2L divided by 2 just gives me L. And that's going to be my width. So now I have this expression that gives me the width. And I can plug that in on the other side in my other equation or my other inequality. So over here, I'm going to just take this value and I'm going to plug it in for W and write 220 minus L in parentheses and keep the rest of my inequality as it was. So I've got L times the quantity 220 minus L. So I'm going to simplify this by using the distributive property. I'm going to have 220L minus L squared. And I want to write my quadratic equation or inequality in standard form. I want all components on one side of the equation. So I'm going to subtract 8,000 from both sides. And if I do that, I'm left with 0 on the left side of the inequality. And writing this in standard form, I'm going to get negative L squared plus 220L minus 8,000. All right. It might be helpful to kind of flip this around so that we're thinking about negative L squared plus 220L minus 8,000 is going to be greater than or equal to 0. So we want to think about where this is greater than or equal to 0. Here with these large numbers, I do not want to try to factor this. I'm just going to use the quadratic formula. So, or I could just plug this in on a graphing calculator, even better. And then I'll just use the trace function to find intercepts. Now, notice because my a term is negative, I am going to have a sad parabola, a concave down parabola. And the x values, the x-intercepts that I get when I put that on my graphing calculator and use the trace function, I get x values of 45.969 and x values of 174.031. So those are possible lengths for my archaeological region. I want the parabola to be positive. I want it to be above the x-axis. So I want values of x between those two intercepts, the 45.97 and the 174.03. So if I just kind of round this off to the nearest foot, which seems reasonable for this problem, I want values of x that sit between 46 and 174 feet. Notice the original inequality sign was less than or equal to, so technically these points should be shaded in here, like this. And we want all values of x that lie between those 2 points that satisfy both of those inequalities. I hope this helped.